Hello, and welcome to week 7 of Reproducible Research in R, a course being taught online through YouTube lectures, as well as some in-person stuff with grad students at Louisiana State University. So, to sort of bring us up to speed, we've gone over a bunch of different stuff at this point. So we've gone over Markdown as a language. We've gone over Git and how to use Git with online repository management systems like GitHub, or there's others, but actually we focused on GitHub. There's like Bitbucket and other things. R as a language, and sort of diving into that. Make files, a little bit of YAML, which is another markup language that's useful. And today we're going to learn, we're going to focus in on some aspects of R. And so last week was a lecture on error handling, line profiling, and code style. And so now that we know the basics of R and how to use it, we can also sort of hopefully hone our skills and write more efficient code. And now this week, I think, is the exciting week for a lot of people that they've been waiting for, which is actually sort of handling data that aren't just silly made-up data like we mainly have been working with. And the data that are not silly or made up are going to be pulled from APIs. So I'm going to go ahead and share my screen and talk about what an API is and how they're useful. All right, so we're going to be working in RStudio. I have the lecture notes up in RStudio. So I apologize for not doing that last lecture. I kept them open in gedit just out of habit. But I think it's maybe a little bit more clear with the sort of larger text within the RStudio environment. And it's just good to sort of get used to this environment, as I imagine this is the environment that many of you will be working in with R through. So yeah, APIs, they're great. So when you don't have the data locally, you can access an API, which stands for an application programming interface. And that's something where the data are hosted online. Why is this good? This is good because the data hosted online may be dynamic. So you may, in order to ensure reproducibility, you may want to query the data often and recompile your analysis such that your analysis changes where the data changes. APIs are also generally well known, or like not well known, they're generally known to be structured in their queries. And so it's only going to give you the data that you ask for, ideally. There's tons of other reasons why APIs are awesome. You do run into some sort of inherent problem in that you're assuming that the API will be, that it is permanent, right? And so that's something to keep in the back of your mind when you write code that queries an API. To do so and maybe cache the data. So save whatever data you end up downloading from the API, just in case it ends up getting pulled or whatever. Yeah, and I think in the lecture notes I go into maybe more detail about APIs. And the general idea, so the computer client makes a request from the web, basically. And so I'm trying to think of it, normal APIs that you would have had sort of contact with. A lot of things that have APIs also have like forward-facing interfaces. Spelled interface is wrong there, fixing that. So things like Spotify have an API where you can access information on artists, see playlists, do other things like, and I think you can actually manipulate things as well through their API. So APIs are not only just good for handling data, but also submitting like requests and things like that. We're going to focus solely on the acquisition of data from APIs. Oh yeah, Facebook has an API. GitHub has an API that we'll go over. And so basically websites like this have APIs because they're looking for people to do work for them, essentially. In a sense, that's a very dark view. But a lot of times they'll have like a developer page where if you want to develop your own sort of app or idea on top of their existing functionality, you can do so. And functionality largely meaning their data, but it's not always that. It could also be sort of create a playlist in Spotify based on some sort of icing or something that the developer would put on top of it. That would query the API. Here I draw the sort of difference between what's called web scraping and working with APIs. And so, for instance, I maintain an R package that queries the global helminth database of the London Natural History Museum. And it's sort of like a mix of API and web scraping. So that's maybe not the best example. So ideally the API is structured such that you submit a request to the website and it has some form to it, which we'll go over later. And typically it returns some sort of structured data just by itself. It gives you just the data. So a web page is HTML, and a web page isn't data itself. It's like a bunch of stylistic stuff on top of what you actually want. So ideally the API returns data in a structured format like JSON. Meanwhile, web scraping is you have to kind of hack away at the HTML or XML to actually get to the data that you want. So web scraping is a little bit less reproducible typically. Not sort of universally. I don't want to say that. Yeah, so a lot of the examples that I've given so far of APIs are things like YouTube or probably Imgur has one, I don't know. But things that aren't of interest to biologists, right? Like if you're, so there's also a bunch of biological data that you can access through an API. So Figshare has an API, which is a data encode hosting service, as well as Datadry, Data1. Neon Data, National Ecological Observatory Network, I don't know. Doesn't have one, I don't think. BN, the Plant Occurrence Abundance and Trait Database, I believe has an API, but I don't know. GBIF, the Global Biodiversity Information Facility, does have an API. So you can sort of dynamically query species occurrences. And we'll actually do that in this lecture. Yeah, lots of museum data and government data. Yeah, so ideally APIs are a step in the right direction in terms of opening data and making it freely available to anybody. And so now that we sort of have a good idea, hopefully, of what an API is, we can talk about how we would go about querying an API. And a lot of the calls they sort of, they have a clear structure, right? That's like the coolest thing about APIs is like there should be very little ambiguity in how the calls are actually structured. And so they're structured as basically queries to essentially a web page. Like it's an HTTP request, hypertext transfer protocol request. I don't like acronyms, so I always try to not use them, but sometimes it's hard to remember what the acronym stands for. So this is an example here. And so this is just an HTTPS address, and it's querying the Google Maps API, which is maps.googleapis. I guess there's more than one. I don't know what else Google has an API for. And then it has these structured commands where it's maps/API. And then, so this part is always going to be, or largely going to be the same. And it's what you put after it that matters. And so I go into this right here. And so this request here is composed of two different parts, really. And the part is the API endpoint, which is this part that I'm highlighting, and the actual query itself, which is the rest of it. And so after that question mark, we have this argument called center, where I give it Manchester, England, and I give it a zoom value, and I give it a total size, I think in pixels. It's really weird size in pixels though. Maybe it's not pixels. And then the overall map type. And so these are just different arguments that the API takes. And these should hopefully be like well documented in the API documentation and sort of how to structure this. But these data live online. And so you're basically just pulling them down into R with this query. But if you type this into Google, I think you would probably get the actual map. I'm doing it over here. Now the Google Maps platform server rejected my request. You must use an API key to authenticate each request. So that's actually a good segue to talking about APIs that are open and APIs that are sort of closed, that you actually need a token for. Which I go into down here. So some APIs require a token, things like Spotify and Google as well. It's easy to get a token. Typically, you just have to fill out a little form, and it's not a big deal. It's sort of like a rubber stamp process, but it's still kind of annoying and does sort of limit the openness and reproducibility of your analyses. So that's sort of something to think about. Yeah, I go into Git and post here. I don't really know if I want to get into that. So you can read that in the notes if you want, but I think that's sort of a little bit beside the point for this lecture. We can go into it more in the Zoom part of this course with the grad students at LSU, but I think it's not really of that much interest, as well as the sort of different types of APIs. That doesn't really matter to our needs. I guess the only thing that matters is that different APIs give you different data formats in return, but the most typical just being a JSON structure. And so this is why we're going to pull in some dependencies. And those two dependencies that we're going to pull in are HTTR and JSONLite. So let's actually run this. I think I already have them installed. I'm just going to cancel that. Let's just ignore that. Error message. And let's just load them in. All right. So I'm using keyboard shortcuts, even though I don't use RStudio, so I don't know how I remember keyboard shortcuts. Control-Enter runs a single line of code. So I'm sending that line of code down to the console down here by hitting Control-Enter. All right, and so for the examples that we're going to go through in terms of how to query an API using the HTTR GET function, which maybe that was why I went into GET and post above, but it doesn't matter, is from the Internet Archive's open library. So this is information about books and authors, years of publication, probably some other stuff. And it has like a forward-facing website as well, but also has that API backend that's completely open. So it's pretty awesome. And so I can show you how that works. Here, we're forming a search based on their API documentation. And so here, this part is that the API endpoint, and then this part is the query. And so the query, I guess it stands for Q. I think I also like specified that it's an author later. And we're basically looking for Vonnegut, which is Kurt Vonnegut, an author of things like Slaughterhouse-Five and Cat's Cradle and a ton of short stories that are fantastic and slapstick and Oh man, what else? There's tons. He's great. I think that's why you can tell that this is why I'm searching, is I'm a fan. And so we submitted this HTTR request and the function get, and now we have this data structure, which is stored as von. And we can look at the structure of von, and we see that it's kind of a confusing structure. And this is because it's JSON structure. So JSON doesn't work well with the data structures in R. So JSON tends to be a lot of nested things, and R doesn't really handle nested data that well, right? You have to, maybe like a list is the best way, and that's what we got, is a list of 10. So a list of length 10 where you have things, and you can use the names argument to von and see what they're called. So we have the URL endpoint that we ended up going, the status code, which is an HTML status code. Is it successful? Was it not successful? I guess those are the two main ones. Headers, which I'm not sure what that is. All headers, talks about cookies, delicious. Yeah, so it has a bunch of different information, and somewhere in there is the actual data itself. I'm looking for it, and I actually, but we have to like extract it, right? And that's what the JSON Lite package is for. Yeah, I said it's basically in JSON format. It is in JSON format, just pulled into R. And so here we'll use JSON Lite package, calling the function from JSON. You can also convert to JSON, which is nice. And then we use, this is also a function in JSON Lite, I believe. And it's called content. And basically I'm trying to pull out all the text from this. And this is going to require some like nuance. So basically I like worked through the documentation and was like, oh, okay, that's how you make a call to it. And this is going to be different, but just sort of trial and error in terms of how you use this part of the function will be helpful. And it'll be something similar to this, as you'll see later on. And there's also many APIs that already have existing functionality in R through a package, like sort of built on top. So you don't, yeah, so this isn't like too overly specific, but it's just giving us an idea of how you go query the database. No encoding supplied, defaulting to UTF-8. I guess that's fine. So now let's see the structure of von info. Should I make a data frame? No, it's just a huge list. It's a very big list. It just keeps on going. So that one simple call that was a list 10, when you actually extracted the text, it has a lot more data within that. There's a list of length 4, each containing a nested list. So we can say length of von info, it should say 4. It does say 4. The first element has a 0 in it. I'm not sure. Let's see if we can get names of von info and see what that 0 is. I'd probably go into it in my lecture notes, but it's actually been a while since I wrote these lecture notes. Something called start. And then we can see num found and again num found. Let's see if I describe it. So it looks like most of the info is in that fourth list element, which is called docs. And this is, again, it's just going to be sort of trial and error in terms of going through and seeing where the data are stored and how the data are structured. And so here, because I think the fourth element of this von info, I think is a list object itself. And that's why we're using sapply on it. And so we can say a class of 4. It is a list. So even that fourth element of a list is a list. So nested lists. The joys of JSON. The joys of working with APIs. And so here it looks like I'm trying to pull out the title information on all of the works that I queried that are written by Vonnegut, or that are associated with the query Vonnegut. And we see like some of them are probably true and some of them are not. I don't think that one is. Not that I would know all of the works. He wrote like a book about, it was like a historical fiction about a pirate. That's probably maybe that. It's like a conversations with, and so that is just a function of our query being not the author of, but or the author of the text, but just being a general query. So it has Vonnegut in the title. Like this is a critical commentary on it. It'll still get pulled in there. Welcome to the Monkey House is a collection of short stories from him. Galapagos is a fantastic book that I just finished reading like a month ago from him. Cat's Cradle on CD. It's another collection of short stories from him. Yeah, lots of repeated records. So we have Slaughterhouse-Five repeated multiple times. And Slapstick, what a fantastic book. And also there's 100 results. This is a function of the package limiting itself. So we should be able to set the limit in terms of how many records we want to actually receive, which I think I do later. I'm not sure. All right, so I'm going to scroll down. Yeah, and so the actual search term Vonnegut doesn't really get us to what we might want, which is a list of all the books written by Kurt Vonnegut that are in this open library database. And so we can look at the actual API documentation, and they have an author argument. So you can specifically say that we want Vonnegut to be the author. And we'll run those two commands, storing them as von2. And we see we should have the same structure, not names, but we'll see the names. Yeah, and we have that same list of 10 things. Gives us the URL, gives us the status code, gives us some headers, what it is, gives us some cookies. I'm guessing the content is within content that we actually want. Oops. All right, yeah, sorry. And so let's run and grab out that information so we can see the length of voninfo2 should be a list of length 4. And now we sort of know how it's structured. We want this fourth element, and we want to grab out the title to see all the works that are written by Vonnegut. And yeah, so Science of Titan in another language. I'm not sure what language that is. We're still getting some things that might not be written by Kurt Vonnegut, but that might be written by Kurt Vonnegut because it has to have him associated with the author field. I don't think that's Vonnegut, but maybe it's a different one. Maybe there's more than one Kurt or more than one Vonnegut. So yeah, that is sort of an example of how you would query an API. And the sort of power that you give it. So I was just looking at title, but really like this voninfo2 object in the fourth, it has a lot of data associated with it. And so let's see, so it'll be a nested list for each entry. Yeah, there's just so much data packed in here. I'm sorry, I'm reading through it. Yeah, so it has information on publisher. I think this is a nested list element. This is 2 levels down in that list. So we have voninfo2 element 4, and then we have element 1 of that. And it probably is even further a nested list because that's just how JSON works. Yeah, so we have all of this information for that single record. We have information on title, author, contributor, publisher, the place, the edition. It has information like the first line of it. It links up with Goodreads, and so if you wanted to have cross like API support or like query Goodreads for this book and see what people thought of it, you could do that. It has information on the first sentence, so you could do like sort of natural language processing on it. Information on, it says person, so let's see what that is. Oh yeah, so it gives you information on characters that are in the book. So this one's Slaughterhouse-Five, and the protagonist of Slaughterhouse-Five is Billy Pilgrim. who often becomes unstuck in time and who survived the bombing of Dresden. And this is the way that Kurt Vonnegut talked about his own experiences living through the bombing of Dresden. And that's my cat in the background. It's my cat falling while trying to, she is not a graceful cat. She's just jumping and falling all over the place, okay? She just wants to be part of the video, so here she is. The least graceful cat potentially in the world. Set her in a chair. So APIs are really useful, really useful for other things as well. And she's opening other tabs. And so here I give an example of how you can query information in a similar structure. So I'm still using the from JSON, still using the content function, and still pulling out text arguments from this call, HTTR call. So we'll add in that code to make sure that we specify the package and then the function. And this pulls in data from, he's sitting right in front of me, from GitHub. And so it's taken a while to run, but it's got it. And now we can look at like different attributes of this. It's probably a list. It's a list of length 10. Response. That's kind of cool. It like nicely formats it for us. See, look at that. Different APIs do different things. And so we can pull out information sort of using that. Let's look at what that looks like. Nested list. Okay, so it's a list of length 22. We can look at the names. And so it saves all the information that is publicly available about me as a user, given my user ID. So information on my login, I don't know what login means, ID, a link to my picture, my avatar, the URL to my GitHub site, things that I've starred, or maybe my starred repositories. Yeah, Twitter, if you provide a Twitter username, your list of like your public repos. So it actually gives a lot of information. Let's see, public repos. Oh, just number of public repos. I have 13 public repositories. It gives information on followers, which are probably also just numbers rather than identities. I have 48 followers. You know that. So it's kind of cool and useful. And so that's sort of, I think we're good in terms of understanding the basics of an API call now. And so we can dig into maybe a more biological example that may be more useful to many people, at least the sort of LSU crowd that is watching this. Yeah, and so I use the information, I use an R package now. No, I don't. I don't yet, I'm sorry. So there's a great API associated with the Global Biodiversity Information Facility, or rgbif, which provides information on species occurrence records. Really, really fantastic. I think they just surpassed, it's like not a billion. It's something crazy how many like occurrence records are associated with this database. Fantastic resource. So we can query it because they have an API. And so this part right here would be that API endpoint, and then species, and we specify the species as a giraffe. So we're looking for information on the coordinates or the data about giraffes. So we can see the structure. Birdie's in my way. I'm going to set her down on the ground. I'm sorry. She's probably going to jump back up here. So let's see what giraffe is structured like. It's been a while since I've looked at this code. So also length, a list of length 10. Oh, nice. Okay, so that's a function of the of HTTR get. How it actually structures the call. And so this is the same structure as we saw in the open library query. So that's good. I feel like I should have known that. And we can look at the content of that, but it's probably just a lot of a lot of stuff. So we'll name it just let's give it an informative name. We'll just call it giraffe 2. And we can use that JSON light, what was it? Extract from JSON, what am I doing? Content, and then it's the content of giraffe. Let's see if we can pull out the text, and we'll hand it this argument. It throws an error, invalid character in JSON text. But let's not even go down this road. So there's sometimes when a lovely group of people that write packages in R to query APIs have already done this work for us. And this is a situation where this is true. And so like the R OpenSci collective maintains a bunch of packages that deal with handling open data and working with APIs. And they have made the rgbif package, and it's a fantastic package to work or to query the gbif data. And so we're going to just make a library call, because I should have it installed on this computer. I do. And now we can use existing R functionality within this package to query information on giraffes. And we can set a limit to 5,000 records. So this may take a little bit of time to run. I make a note here that depending on your OS, there's some dependency issues. Oh, I didn't realize that rgbif actually, it requires the rgeos package to be installed, which there's some R packages that rely on C code or C libraries that are expected to be on their machine already. And the geos library is one of them. So a lot of the spatial libraries that R interfaces with, like GDAL, GDAL, you need to have them before you utilize the functionality that's built on top of them as an R package. And that gets you into a situation where containerization is a much better solution for reproducibility. And we will go over containerization, I think, in a later lecture. Yes, I waffled on whether I wanted to talk about it, because it is somewhat tough to like sort of wrap your head around, and yeah, for a whole number of reasons, but I'm going to do it, and it's going to be fun, and I hope it turns out well. So, but that's like weeks from now. But yeah, so the data now finished running, and we have this giraffe object. So we've overwritten what we had previously, which the object that we called giraffe, and we see it's this huge list of data, and we can see what the length is. It's length 5. Let's see what the names are. It's got some metadata. It's got a hierarchy, which maybe is taxonomy or something like that. It's got the actual data itself. It has media associated with it, so maybe images or something like that, and then something called facets. So let's see what the data are structured like. We can say what class is giraffe data. It is a data frame or table df and in dplyr terms. I think that's a dplyr created object. Yeah, sweet. So that gives us information on the scientific name. So we only queried one species, is giraffe. So that's just a redundant column. Information on where this individual was recorded. Things about data set key, installation key, protocol, last call, a ton of information. And so all of these are different columns of data that we get back. So when it was geo-referenced, sort of different QA, so quality assurance or quality control of data. Yeah, information on life stage and sex. I actually didn't realize that it had that information. That's actually kind of cool. Let's get out of here. Let's actually explore the sex data really quick, or the life stage data. All right, it's actually like pretty well resolved too. So if we see table, then we can see the breakdown of different. All right, so ignoring NAs, we got information about on half the data, because it's a limited to, or let's see, we can see how many entries there are. There are 5,000. So we limited it to 5,000 and it pulled 5,000 occurrence records. And I guess right around half of them, a little bit less than that, have information on the giraffe sex, which is that's pretty sweet. Did not realize that was a thing. We have to like use that in the future, right? What if you trained a species distribution model on only males or only females? There's reasons why you do that. That's a little bit of a silly example. Yeah, and so I've been trying to use a lot of these base R commands that we learned in the R introductory lecture to try to get you thinking and like of how to interrogate the data. So once we're requiring this data from an API, we get these data. Let's see things about them. So like check out their dim, check out length, check out class data. Start just like get your hands dirty and play around with the data. Oh, all right. Yeah. And so this is the same thing as just what we did, except now I just return the data itself, which is just this giraffe data list element. All right, I'll still query it using that. It's just going to work its way through. So now I use yet another dependency. We're going to see how it just piles up, right? Our session info is going to have like 20 packages in it. It's not really ideal in terms of reproducibility, but we're going to work on making sure that, that everything's reproducible using containerization and other approaches. So while this is downloading, one thing that you can do is at the end of every R Markdown script, run your session info command. It's something just really simple. Just type in that right there that I have, the session info function that provides information on what packages are loaded in, what OS are you running, and what version of each package there is. And so this is still running. It's taking a long time. Maybe it's my internet connection or something. So I got a warning message. I'm going to set Brody down. She's stepping on the keyboard. It's so standard. But it's probably fine. So now we can load in. Let's see if it's fine. We can load in the maps package. And the map select package is really great for making just really simple map visualizations. So the default, without handing it any arguments, just gives you the borders of a global map, which is right here. And then we can use, so we're actually going to go into visualizations shortly after this, and we'll go over these functions in a little more detail. But basically this sets up the plotting environment, this map argument. And then on top of that, so it sets up a workspace or a plotting space that corresponds to latitude and longitude. And so we can use other functions that layer data on top of this base map, like points, and hand it latitude and longitude arguments, and it'll plot points of where giraffes are given this query that we've made. And so these other two arguments that I give it, this PCH corresponds to point size or point type rather. And so the default is open circle and PCH16 is a closed circle. It just looks a little better in my opinion. And here the color that I'm handing it is a gray with a alpha channel of 0.5. And this is also just because I think it looks good. It's not necessary to use this. So the gray is the only thing that exists as a function. Other colors are specified just with characters. And there's a list of characters, of different characters that R knows. You can also use numeric indicators. So 1 corresponds to like a royal blue. No, I'm sorry, what am I talking about? 1 is black. I think 2 may be a royal blue. 3 is a red. 4 is this really ugly green, I think. Don't quote me on that. It's been a while since I've used like sort of base, just like default plotting colors, because they're hideous. They're awful. They're so ugly. That's me. They're not that bad. Yeah, so we've plotted these points on top of this base map, and we see that giraffes are largely in Central and Southern Africa, but are also just hanging out not too far away from Louisiana, hanging out a bit in California, and are also in what looks to be like Maine. So don't trust data from APIs. These are most likely zoo records. Potentially they're errors, but don't inherently trust data from APIs. This is a sort of good example about sort of sense checking your data. Oh yeah, so now I actually go into, before we go into plotting and visualization stuff, I'm going to talk about interfacing with databases. And so APIs are these things that exist on a website and that you pull data down from. There's also data that you might have locally that you want to interface with. And that data could be in the form of a CSV, which is a traditional sort of data type that you'd want to load in which case you just say read.csv, and then you provide the path to file. And you read it in and store it as an object. I call it DAT or something more informative than that. But there's some cases where the data aren't formatted in a CSV. They're structured in a way that is nested, like a lot of the calls and a lot of the JSON calls are. And that's the sort of the way that databases inherently function. So databases often are a way to relate relational data. So things where you have different hierarchical levels of data. So here we have information on giraffe occurrences, but what if we also had information on giraffe phylogeny or species level traits of giraffe? We wouldn't want to mash that into the same data frame that contains the species occurrence records, because that would just be repeating a bunch of data, right? So ideally, we'd structure our data in a way that is efficient in its terms of storage. And so we'd use some sort of key that is shared between both data frames or tables, like species or something like that. And that allows us to relate both of the data structures or data tables to one another. So if we wanted to pull out trait information and join it with the occurrence records, we have that ability. Yeah, and so this is another dependency that we'll be installing. So I think I'm up to maybe like 4 or 5 dependencies at this point, plus associated packages. So all these tidyverse packages. And that's not all from tidyverse stuff. That's actually not at all, or mostly not. We can't really blame tidyverse for that. Some of these packages are definite tidyverse, but some are probably a function of rgbif, maps, and then the 2 packages that we use to query APIs. But probably mostly these first 2, actually, if I'm reading it right. But that's neither here nor there. Basically, we have a lot of dependencies in the old workspace right now. All right, I still haven't even loaded in this DB plier, and so that it follows the syntax of the plier package, but now it's DB standing for databases, or database, and that is how we're going to interact with a relational database. And so here we actually didn't add any sort of these suggests or whatever. We just added one attached package that is required. Did I spell accommodate wrong? How do you spell accommodate? I was missing an M. I don't use a text editor that has spell check, so I make a lot of spelling mistakes. I'm dumb. So yeah, the DB plier package works or allows you to work with a lot of different types of databases. So database, you can't just add a database. There are many different sort of subtypes of databases. And so there's SQL-Lite databases, MySQL or MySQL databases. I'm trying to think of all the other ones. I list a bunch here. And so basically these are all different R packages that connect and interpret different forms of databases. So a Postgres database, etc. we'll be using R SQLite as a backend, and so this is an SQLite database that we'll be working with, and this will require another dependency, and so yeah, it's as it suggests, but we're going to load it into the workspace. SQLite. All right, and then we can see our session info, and now we have it. Major version 2, minor version 2, patch 0, semantic versioning. We went over that previously. All right, and so I think this is actually already done, but done for me locally. But you can follow these codes, and what follows code, and what it's going to do is first create a folder in the directory that you're in called data_raw, and then it's going to download a file from a website. It's downloading a file from Figshare's server. It's not really an API, is it? Can I call it an API? I don't know, maybe. But the output is going to just download the file portal_mammals.sqlite. And so this is data as part of the Portal project, which is small mammal trapping in New Mexico. I don't know where I actually got these lecture notes are adapted from somebody. I think I give them credit later on, but it's likely Morgan Ernest or Ethan White or people associated with the Portal project. And so they run the We Ecology Lab that does a lot of really cool stuff, and including sampling these small animal communities as part of the Portal project. So we can run this code, and it's just going to recreate things that I already have done, but I actually want to make sure. Let's see what my working directory is if it opens. Oh yeah, okay, so it says that I'm on my flash drive in my teaching folder of this flash drive called Euler. I'm in my Reproducible Research folder. Yes, that's still, let's just run it. It's just going to re-download the data. And there it goes. So now I have a database. And now we can connect to that database using the DBI package, which is installed. Is that just another dependency, or is that? Yeah, we didn't load it in yet. So actually, let's load that in. Sorry about that. I'm going to add an install packages command and a library command to DBI so that this code will actually run on any machine. And we're going to use sort of the db connect function from DBI, which I imagine stands for like database interface. And then we're going to specify that this database is SQLite, and that's we're going to use the function that reads in SQLite database or refers to the SQLite database because we don't actually read it into memory in R, which is actually one of the sort of best parts about working with databases in R. R has to hold objects in memory. So when you have a really large object and you want to sort of subset it or get at summary statistics or things like that, you have to have a computer with a lot of memory or to connect to a remote computer that has a lot of memory in order to access and examine those data and subset those data. But here, by using and interfacing with SQLite databases, you sort of get around a little bit of that by holding the object outside of memory. There's also a ton of R packages that are useful for handling larger data objects and holding things outside of memory. So like raster, for instance, holds raster images outside of memory. All right, so now we have loaded in mammals. Sorry, I went a little bit too fast. We can see mammals is an SQLite connection to this file. And then we can use the source_dbi function from dbplyr to, I think it just gives us, yeah, so it just gives us information about mammals. And it gives us information about what tables, and now it should allow us to start interacting with stuff. Yeah, so it basically gives us information that there's 3 tables: plots, species, and surveys. So the way the database works is you have a higher level sort of database that is composed of multiple tables, often composed of multiple tables, not necessarily. And then each table is connected by some sort of key that relates the different tables together. And you can use, okay, so you can use dplyr, which we've used previously, and specifically the table function to interact with databases. And so we've loaded this data, we use this mammals as a database object. So it's just a pointer, basically. It just says like, where is it? Yeah, oh, here it is. It's just saying like, this is a connection to a database. We're connected, that's the path, but it's not in memory. There's no data in memory right now. And so the dplyr command, so we load it in as a table, and we can make a query either in sort of traditional R syntax or in SQL or SQL syntax. And so SQL or SQL is pretty much just like 4 or 5 verbs. So if you want to learn it, it doesn't take that much time to learn, but to write like complicated queries like takes some time, because like it's a weird kind of like flow to it, but it's fun. I got decently good at it a while ago, and now I've mostly forgotten most like what I sort of know. But basically, select is the same thing as select in dplyr syntax, where you're picking out specific columns. From just tells you what data are you pulling from. So surveys here is a table, and I am pulling out 3 columns: year, species ID, and plot ID. All right, so when I run that, it actually, I don't know why that didn't output down here in the console, but it's going to just output here and show us the first 10 out of, I guess, just 1,000 rows, and it contains information on species code, which is, I guess, probably just first letter of genus and species, information on what year it was sampled, and then information on the plot ID. And one thing that's really nice about relational databases is a lot of times there's like a metadata table or something like that that'll like sort of link and provide a little more structured information on what plot ID is. Whereas a lot of ecological data that you just like download from Figshare may not have that metadata, and so you'll just be sitting there scratching your head being like, plot ID equals 2. Like, all right, I don't know what that means, but let's do this. But you don't have to use that sort of SQL or SQL syntax. But when you don't, you'll have to pull the object into R, which means taking up that memory. And so being cognizant of that is good. And so here we can name something surveys, and what we're going to name surveys is the table object surveys from the relational database, mammals. You can run that, and now if we say structure of surveys, we see that it is a list of length 2 with information on the SQLite connection, and I actually didn't expect that. That's kind of nice. So maybe it didn't actually pull it into memory. I thought that it would have to pull it into memory, but this still looks like a pointer because it's saying what the database name is, and it doesn't look like it has any like data associated with it. Because normally you'd see the actual data, but no. All right, so just kidding, sorry about that. You don't have to pull it into memory. Yeah, this didn't change. So here I'm running basically the same commands as before, where now I'm just trying to subset down to these 3 columns. Columns of year, or select, that's gonna, I'll call it subset. I'm going to select year, species ID, and plot ID from surveys. And it looks the same as the SQL or SQL command above. And we can base our functionality on this object. So we provide head, and it gives us, but it looks different than just like a data frame. And so this, I guess it's called a lazy query. I don't know what that means. And it gives information on where it's pointing to, and then information. So I didn't save that. So this is just subsetting the data, but not storing the data. And so surveys still has multiple columns that are not just those three. And so here we see, when I look at the head, which is the first 10 lines of the surveys table, it gives information on record ID, which is just going to be 1 till the length of record ID, or the number of rows in the table, likely, not actually sure. Information on month, day, year, plot ID, species, sex, hindfoot length, it's important for rodents, and then information on weight if they had it, but it doesn't look like they have it for the first 10 individuals. They might have it for others. And so we can use this to sort of look at, or this is just a sort of example of other dplyr structured commands that we can use. And this will still just give us a pointer to the database, not actually pulling the database into memory. So here what I'm doing is, what if we only want or only care about individuals whose weight is known and whose weight is less than 5, which I guess the unit is probably grams. So it's a very small mouse, or a rodent, I don't want to call it mouse, small mammal. It's called small mammal, just in case there's other things in there that aren't rodents, because I'm sure there are. And then we want to select 3 different columns. We want to select species ID, sex, and weight. So this is the piped syntax that we went over a little bit, where we take the surveys object, and you can read this pipe as basically and then. So let's take surveys and then filter this surveys object down to just rows corresponding to weight less than 5, and then only selects columns, species ID, sex, and weight. So let's run it and see what it gives us. We'll use the head command again, just to explore the data, make that lazy call. And yeah, there's some that are in there with weight of 4. Oh, man, that's grams. And that P makes me think it's Peromyscus, which that's a tiny Peromyscus, that is a tiny mouse. Peromyscus being a genus of small mammal. And that's probably Reproducible megalatus, which are super duper cute, but are like a little bit smaller than most of the Peromyscus that I know, at least. I don't know. Yeah, so we talk about lazy calls until you make it not lazy, right? Yeah, it's funny. So I can't act on the data itself. I'm showing you the head and it works with that. But if I tried to say like surveys to column 1, I don't think it'll provide me with that information. Yeah, it'll say, no, like, get out of here. The surveys to object isn't a data frame. Stop treating it like a data frame. So it's held outside of memory. So to pull the data into memory, first, we probably want to subset it down, right? And so we've already subset surveys 2 down, right? Yeah, we filtered it by weight, and then we only selected columns that were important to us. And that's important because maybe that full database is too big and we just really only want this small bit. And so we can use the collect function, which I'm going to look up where it is so I can actually make the function call. It's in dplyr. For some reason, I thought it was going to be in dbplyr. So we can scroll back down and use the specific function call or specific package call to do this. And then we can now see the head of surveys 3, and it gives us the data within R. So now it's pulled that data from the database and now holds it in memory as a data frame. So if we said class surveys 2, we're going to see it's like an SQL connection or something like that. Yeah, table DBI, table SQL. But if we see the class of surveys 3, it's a data frame. Or a table DF, which is just dplyr's gravy on top of a data frame. It's probably a tibble is what we're looking at, right? Yeah, we're looking at a tibble, which is just a bougie data frame. Yeah, we can see that when we try to like specify a column. And so despite both of them looking sort of similar. Right? If we say surveys, head surveys 2, head surveys 3, it gives us what looks to be the exact same information. It's the same structure. And yet when we try to call out specific columns, surveys 2 provides us with a null, and when we want to query just the column sex, and surveys 3 actually provides the data on sex of the small mammals. Yeah, and so I wanted to talk briefly about linking the idea of joins. So joins, the idea of joins originally came from SQL or SQL. And so dplyr sort of adopted that. So now let's pull in, so we have surveys, we have the survey data, which corresponds, we've hacked it down to just species ID, sex, and weight. And now we also have this plot level data that gives information. So yeah, nice. So it gives plot ID, which is just numeric or integer value, 1, 2, 3, 4, up to 10, and then the plot type. And so that these are some long-term exposure plots, rodent exposures, control plots. So these all deal with the actual manipulations that were performed as part of the portal project. Yeah, and then now we can sort of join these data together. We couldn't join it together with surveys 3, right? Because we actually only have information on species ID, sex, and weight. In order to do a join, the two tables or data frames have to share a column. Normally that column is a key. And so we see if head of surveys 2, it should have a subset, sorry, head of surveys, that's right. It has a plot ID column. And this has a plot ID column. And that's the way to make the join. That's the way to relate it back and get at the actual plot type in the data. And that's what I do. I thought surveys, will that work? Let's find out. Oh man, it does. I honestly, oh cool, okay. So that's still a lazy query. That's really cool. I didn't know I was gonna do that. I'm sorry. So we have, okay, so here's what happened. We have surveys, which is being held outside of memory. It's this data frame, where it's just a pointer to this SQLite object. And it's a table called surveys. And then we have plots that we read in, and plots is also a pointer to an SQLite data frame, sorry, an SQLite table that is part of this portals_mammals SQLite database. And we can actually use existing functionality from dplyr to join these two tables by their common key value of plot ID, sorry, not key value, their value, their shared column of plot ID. And now we have a new lazy call that still everything's being held outside of memory, so we're good there. That joins the two, and now we have this plot type variable added to surveys. So remember, this is a left join, and so it's going to maintain the same size of the first table. So basically it's saying, take that first table and then take this other table, and based on that key value, the value match between this other column, just sort of like mash this other table in and fill in the appropriate values given that sort of archetype of that first argument, that surveys table. Hopefully that made sense. Nice. And if we wanted to collect this and pull it into memory, we could just use the dplyr collect function surf plot in order to like plot it out or work with it. But let's not do that because I think I'm going on a bit in terms of the length of this. So now I want to talk a little bit about visualizations in R. We can go into more detail on visualizations in class, in the Zoom meeting that I call class later, because there's a lot of different ways you can make visualizations, and you have to sort of think about what you're trying to communicate. And so one of the readings this week really talks about that. Not plotting from like a just straight code perspective, but plotting from a little bit of a what information do you want to communicate with the plot? What is too much? What is not enough? how many levels of sort of complexity can you bake into the plot without it being unintelligible. Yeah, so like Excel 3D bar plots are a good example of unnecessary thing, right? You don't need your bars to be three-dimensional. It's a visualization that actually detracts from your main point. And we'll talk a little bit about that, but not too much about like the philosophy of plotting, things like that. There's also a lot of different packages that work with different, or not work with different data, that make different forms of plots. And so there's sort of the two, I think, main schools of plotting. So we were going to ignore lattice plotting, and we were going to ignore audit spatial plotting, and there's probably some other sort of packages that do plotting. I don't know why I can't think of right now. But there's just sort of like the base R plotting, which I'll go mainly over, and then there's ggplot2, which a lot of people start with it, actually to teach with. I am not a huge fan of that because it has syntax that's just really specific to ggplot. So I worry that students might learn just ggplot syntax and then not be able to translate that back over to make a plot outside of the ggplot framework. And also, I think ggplots are just freaking ugly. They're just hideous. But that's like a personal preference thing. They can be pretty, but like, they can also just be ugly. Just hideous. Yeah. So I'm going to teach you base. I'm going to teach you base plots, which gives you full control over every aspect of the plot, which I don't really think that ggplot does effectively. So most of the time when you like search for like plotting advice on like Stack Overflow, it's people just being like, I tried to make this with ggplot and I failed. How do you do this? And that's more of a sign of, that's either a sign of the adoption of ggplot, so ggplot into people's sort of tool belt, or it's a sign that ggplot is opaque as shit. Maybe both. All right, so let's go into base plotting, and that starts with the plot function. And the plot function is great because unlike ggplot, packages can build on the existing plot functionality. And so plot is actually like it's a function, but it's a type of function that can be ported over. So for instance, plotting network objects in R, you use plot.igraph, but you don't need to put that .igraph. Oops, I don't know why I just printed out the function. I meant to actually have a question mark there. And so if you have an igraph object and you use this S3 method, or this sort of base function plot, it'll work and it'll do its thing. So you can build on it, which is very nice. And that's not really something that I don't think you can do in ggplot. All right, scroll down. So let's just, I don't know why I moved that out. I'm just going to come back. So this is an ugly plot, but the plot function works. And so it's taking x and y, or it's just taking x, I guess. Or sorry, just taking y, I guess. And it's plotting a vector of 1 through 10, indexed by 1 through 10. And so this is the same thing as if we said y equals 1 through 10, x equals 1 through 10. Why isn't it showing up? Thanks, RStudio. So here it is. That's an ugly plot with all the defaults built in there. So we have our PCH, which we talked about earlier, as 1. So it's default to open circles. It defaults to give access labels that are the values that I give it. So it'll just say the vector 1 through 10. If I named that vector, it would just say the name, which is fine. But it's an ugly plot, admittedly, as I note here. But the great thing is we can make it prettier. There's tons of functionality within the plot function that we can play around with. And this is sort of demonstrated by this is actually a decently short help file for such a easily tunable or broadly tunable function as plot. And so here I've done a bunch of stuff. So let's shrink this down. So here now I'm plotting an x variable, so your x-axis is 1 through 10. My y variable is 10 poles from a random uniform distribution bounded between 0 and 1. The type, B stands for both, so that's talked about, excuse me, right here. So P is for points, L is for lines, B is for both. So it's going to draw both points and lines connecting the points. I specify my X label and Y label with X lab and Y lab. And then I use PCH and hand it a vector. So you don't have to hand PCH or a lot of these arguments a single value. You can hand them a vector of values of equal length to your input data. So that's a vector of length 10. This is a vector of length 10. I can hand it plotting arguments that are vectors of length 10. And I do that not only for PCH, which controls the point type, I also do it for color. Color specified as COL, col. And lastly, I change LAS to 1. That's just my own personal preference. It turns the y-axis labels horizontal, which I think enables a little bit more readability. So let's see how that looks. And there we go. I kind of don't like that it's rendering within the document. All right, but here we go. I'll move this down. And here we go. It's sort of an even uglier plot, but now we're seeing that it's actually more tunable. And so we changed the Y label, we changed the X label. These are all not all, there's a bunch more different plotting symbols. These are the base R colors. And I was wrong about that royal blue being corresponding to 2. That actually corresponds to 4. So black is 1, red is 2, horrible green is 3, royal blue is 4, and then it sort of goes off into the deep end. I don't know why that's also black. I guess there's only like 6 colors in base that I can access using just numeric values. Yeah, but plot isn't the only thing that we have at our disposal, because you may want to make a different type of plot. And so plot is good for X, Y plots where you want to draw points in space or lines or things like that. But if you want to draw something like a bar plot or a histogram, you'll want to use hist or bar plot. And then if you want to do an image plot, which is also sometimes called a heat map, you can use the image plot. And so that is, you hand it a matrix and it has, it bins each cell as a point or as a box on a lattice, 2-dimensional lattice. And then colors that point colors each box in that lattice based on the value within the lattice. Which I realize that sounds actually really confusing, so I'm just going to quickly show you what that looks like. So let's make a matrix of 10 columns and 10 rows that consist of random draws from a uniform distribution. We'll call it mat. We can see mat. There's mat. It's a matrix. And now we can say image mat, and it gives me this garbage error, but you never see that when you don't use RStudio. Isn't that crazy? See if we can just do it again, and now it actually plots it, and that's what an image plot looks like, or a heat map looks like. All right. So there's all these other plotting functions, and there's also higher level functions for how to actually organize the plotting space. So this plot is bounded like right here, right? This is the actual plot that's being drawn. But there's a lot of meta things that I can control about the plotting space, like what's up with all this white space? If you can see my mouse, which I hope you can. So white space at the top, or the bottom, or the left, or the right. Things like inner margins, outer margins, overall size. When you start to do multi-panel plots, you can control height and width of different panels, either using the layout function or sort of within, I think you can do that within par. So par is an incredibly useful function to sort of play around with and get a good idea of what it's doing. And so here, I'm just going to do this sort of by example. I'm setting the margins of par, and I'm setting the margins to 5 units or lines. How margins work is you give it a value of length, a vector of length 4, corresponding to bottom, left. I hope that's a weird video thing. Left, select your y-axis, which is this part right here, if you can see my mouse where the values are, where the y-axis labels are. 3 is the top, and then 4 is the right-hand side. So we can set that, and now we're going to make a histogram of 1,000 draws from a random uniform distribution. Main sets the overall label, so that the title of the plot. Border sets the color of the borders of the histogram, each bar. LAS, as we've gone over, turns these horizontal, these y-axis labels. I provide an X label of uniform distribution, and I set the color of the actual filled bars to be Dodger blue, one of my favorite colors. And I use the adjust color function to set the transparency of that to 0.25, which gives it a nice little effect. Completely stylistic. Let's see what that looks like. Looks like nothing. It didn't plot. Oh, it's plotted down here, isn't it? You're killing me, RStudio. You know what I'm gonna do? I'm gonna copy and paste it into the console, and then maybe it'll toss it over here. Yeah, cool. That is not that par. That shouldn't be those massive margins. We can play around with it though, and you can see the effect of the margins if it's actually doing it right. So here I'm setting the margins to be much bigger on the X and Y axes, and then the top and right side of the plot will be rather small. Oh, yeah, it actually does work. It didn't look right. So this actually looks really low resolution. So I'm used to plotting directly to an output object. Like, I don't show you how to do that. I'll go into it very, very briefly now. So you might not want to interface with this RStudio garbage, but actually just write directly to a plot. And so typically you want to write to something that's a vector graphic. So I like to use PDF because it sort of preserves, it doesn't have any like resolution problems like PNG and things like that. So you can use the PDF function, which basically think about PDF the function as like opening a PDF, and then whatever you submit to what would be plotted afterward gets put into that PDF. And so the things that we have to say are just things like the file name. We can also specify information on resolution and other things like that. So let's just give it test.pdf, which is a silly name. And we have to end the device, right? You have to say like at some point, like stop writing to the device, you're done. And we do that using dev off, which I think we can do within RStudio, but hopefully it doesn't crash it. Hopefully it'll just shut that. Yeah, so it shuts the plot on the right down. Gets rid of it, and that's something I'm not going to really talk much more about. So if we run this, it shouldn't actually plot it within this or within this, but now it writes the file. And we can now see this file as written, but I'm not there. Where I'm not in. It's my working directory. Oops, I said set. I want to say git. So this is my working directory. So within that directory now, there is a file called test.pdf. And so we can go over and change into that working directory. Now we're in that working directory, and we see there is in fact a file called test.pdf. And we can open it from command line using, if you have events, I do, it's my PDF reader. I'm going to open it using that, and now we see it's pretty, and it didn't have to go through the silliness of exporting it using this little point and click garbage. That's too judgy. I'm sorry. You can you can do it however you want. I like that. Using just like straight to PDF, you don't have to. Let's close that. All right, so now I'll briefly talk about how to make panel plots, but I won't go into it. We can go into this more in detail in the lecture. We can do some live coding and kind of mess around and just like get more experience plotting. Because plotting can be something that's really frustrating, but it's also something that's really rewarding when you make like a really pretty plot. Like, yeah. And hopefully you do it outside of things like a vector graphics editor like Inkscape or I don't know, editing your stuff in PowerPoint, right? Because we want it to be reproducible end to end, which means your final figures should hopefully, and I'm guilty of editing, post-processing and editing as well, but hopefully will be something close to sort of what you have. So here I'm using the layout function. This is, yeah, I think this is actually completely equivalent to using to setting up your par and then handing it or using the mf row argument, which stands for mother freaking rows. I'm just kidding, it does not. What are you doing? There's a window right there and Birdie's sitting in it. And you would specify the number of rows and the number of columns right there. Oh, but I like using layout because it's a little more flexible and that allows you to set heights and widths of each of the each of the elements, or each of the elements, each of the panels. Let's call them panels. And so here we hand lay out a matrix of different sort of values and structures. And so we hand a matrix of, and I'll run this code so we can see it. And it doesn't run it because it's stupid. So I'm going to copy it into the console. Oh, it ran in the console. It's a matrix of a 2x2 matrix containing unique values in these. And so these are unique values setting up the different panels. And so if we run this, it'll return nothing, but it'll set up that plotting space. And now we can plot within that plotting space. So let's do a histogram from a uniform distribution. And it plots it across the whole area because it is awful and I hate RStudio. So it's just failing right now at using the layout function. So let's copy this and see if we can't get it to run in the plotting environment over here. What is it doing? This is what I have to work with, guys. I'm dying here. Let's just use the PDF and write it to PDF. So then we say panel plot.pdf, and then we can run this, and remember dev off at the end. And we're doing 4 different distributions. We're doing a uniform distribution, we're doing a Gaussian normal distribution, Poisson distribution, and an exponential distribution. So a histogram drawn from data from all of those distributions. We can run that. It goes all the way through, outputs, and then it gives you information on what level your dev's at. So we're back in a null device. All graphic stuff has been shut down. And now we can go to our console. We can look at what we have in there, and we can have the events, except now we have named it panel plot.pdf, open that up, and boom, we got a multi-panel plot. So for each one of those plotting objects, we can set the par. So we can set these margins of each of these panels differently. We can control the width and height of the panels and individual aspects of the plot, for instance, color of bars, type of plot, etc. And so now I go into a little bit of detail on how to sort of build up from a base plot, further demonstrating the flexibility of the base plot function and the different things that you can do with it. So if I ran that, yeah. So this is that plot. It's nothing. I said axes equals false. I said don't plot the points. So we're using type N. So it just has very little information, but it sets up my plotting workspace. And now I can use the points argument to set up points of 2 different colors. It says plot new hasn't been called yet, which is garbage. It has been called. I called it right there. So that's whatever. That's a thing. And then I can set up the axes. And so these are all things that can be called after the plotting environment is set up, which I did right there. In addition, you can use like the text argument to place some text on the plot, wherever it is in sort of this space, which is defined as 1 to 10 and 1 to 10. And then you can also include the legends. And so I included syntax on how to include a legend here. You can provide it a relative place to put it. You can provide information on what the legend item should say, and then differences in terms of like color or line type, line thickness, point type. So PCH, I set the same for both of these, but the colors were different because the point colors were different here. So here I set the color equal to 1 for those points and color equals to 2 for those points. And then lastly, I just want to bring to your attention that there's a lot of different color packages out there, and some of them are better to use when dealing with or making your research and plotting accessible to people with color blindness, or people like dealing with black and white printers who want to print the article out. And there's a bunch of other like reasons why you'd want to mess with colors, but keeping that sort of in the back of your mind is important. And the package that is good for using, or that is, I think all their palettes, oh, they have that, yeah, I'm sorry. They might have not colorblind friendly palettes, but you can specify colorblind friendly equals true within the R color brewer package, which is a really versatile package for looking at or exploring and creating different palettes of colors. And there's also many base color packets. So like rainbow is a base color palette that you hand it the number of colors that you want, and it gives you those hex codes that R can interpret. So you can hand R a numeric value for a color, which is really ugly and dumb. Don't do that. Not dumb, really ugly, arguably. You can hand it a character, which says something that is a color that R knows. So things like fire brick 1. And there's a whole list of R colors. So if you Google colors in R, it'll show a PDF of all the colors that R knows. And they're basically just ported over from HTML. So Dodger blue is something that's base HTML color that everyone knows, that HTML recognizes. But yeah, you can also see, you can use display brewer all to see the colorblind friendly palettes that are associated with them. And then you'll just call them out by this, this palette delineation or definition. So set to, paired, things like that. Okay, and I think that's all I had. And so hopefully I didn't go too long. We'll go over more detail in class, but hopefully this has been enjoyable. I'm sorry I struggled a little bit with RStudio's interface. I'm just used to writing directly to PDF or running R in the terminal where it opens a new window to plot in. So that's sort of my mistake. So yeah, I'll stop sharing my screen and hope you guys enjoyed the lecture, and take care, and I'll see you next time.